Alright, I'm going to explain to you all how to name binary molecular formulas today, and I'm going to do it without the slides from the PowerPoints. I'm going to try to do it with just explaining it to you. I think that's going to be better for you. And to do this, let's remind ourselves what binary molecular formulas are. They are made up of only two nonmetals that are different. Okay, so we're not talking about the diatomics here. We're not talking about that Brinkelhoff family we were talking about. We're not talking about if they're homonuclear here, where they're the exact same element. We're talking about two different elements, and they are named. And remember where the nonmetals are. They're on the right hand side. And we're also going to keep in mind that the noble gases, which are very, very stable and they don't generally form compounds at all, they're not going to be included either. So we're talking about a very small range of elements in this situation. But we can still form a very vast number of compounds because you can take, since they're sharing their elements, just like well, in a very overly simplistic way, you can share your pizza with your best friend, or you can choose to share your pizza with your sibling, one of your siblings, if you have more than one. You can share your pizza with another friend. You can share your pizza, if you have one, with in a lot of different ways. Perhaps you have a small pizza, and today you eat two pieces, and you share your with your spouse, you share the rest of your pizza. But in another day, you're quite hungry and you eat 5 slices and you give the other 3 slices to somebody else. So you can see how sharing can be a different entity. And that's exactly how things happen. So I'm going to explain this using carbon and oxygen. There are two compounds that can be formed with carbon and oxygen. There's carbon with 1 oxygen, and then there's carbon with 2. Carbon monoxide is very poisonous to our systems, and yet carbon dioxide is very healthy for us. We give it off, and plants use it in photosynthesis. So these two are extremely different from each other, and yet they contain the same two nonmetals, carbon and oxygen. So carbon has 4 valence electrons. Here are its 4. I'm going to use X's to distinguish. And then oxygen, if you'll look on the periodic table, you'll notice that it belongs in family number 6, which means it has 6 valence electrons. Now it strives for 8, and in this sharing situation, oxygen feels the effect of 8 because it's sharing. But poor old carbon over here, it still only feels 4. So we can fix this if we will just move some of these of oxygen around a little bit. So let's move some of these of carbon. So here's 2 of oxygen, carbons, and here's 4 of carbons. But if we move these 4 of these of oxygen, I hope you can see these. Now, here are 2, let me circle them, 2, 4, 6, 8 that oxygen is still feeling. So it's happy. And also here are 2, 4, 6, 8 that this carbon is feeling. So they are both feeling the effects of 8. So they are maintaining that octet rule, feeling the effects of having 8 valence electrons, which is what they would like to have. By the same situation, you can have this carbon, which has its 4 valence electrons, and it can share, instead of sharing them with 3 sets of electrons, this would form a triple bond. Here I'm going back a little bit. It would form a triple bond with oxygen in this case, or in the case of this carbon dioxide here, Here are oxygens, same 6. If we were to instead move these outside ones and place them in the middle, now each is feeling the effects of 8. Here are our carbons, 8 that it's feeling. This, let me redo that one. I didn't draw that. This oxygen here is feeling the effects of 8, and so is this one over here. It is also feeling the effects of 8 electrons. So everybody's also feeling the effects of 8. So this carbon dioxide's structural formula would be 2 double bonds on either side. So they're both equally sharing their electrons and equally meeting the criteria of sharing. But they're doing so in a different way. Now, how do you know? If they both have carbon and they both have oxygen, you have to come up with a way to name them. And so there's a systematic way of naming that we use, and it's called chemical nomenclature. And so the prefix system is used with Greek prefixes, with using mono, meaning 1, di, meaning 2, tri, meaning 3, tetra, meaning 4, penta, meaning 5, hexa, meaning 6, hepta, meaning 7, octa, meaning 8, nona, meaning 9, and deca, meaning 10. You would use these prefixes to simply explain or to identify how many atoms of each element that are present in the compound. Now, traditionally, you do not use mono for the first element. So even though this could be monocarbon monoxide, you do not use mono if there's only one for the first element. So this becomes carbon, and that mono is understood for carbon. There's only one carbon. And then you would say it's really monoxide, but then that would become monoxide, and that sounds funny. So they drop one of the O's in the middle, monoxide. And this mon means one oxide. And all diatomics are going to end, two-element binary, two-element compounds are going to end in IDE. You're going to change oxygen to oxide. And they will all be like that. So naming molecular compounds is actually fairly straightforward. We're going to work a sample problem that's on page 55 of your text that asks us to name some of these practice problems. Like on page 55 is where I am. It gives us Cl2O, and it gives us SiCl4. So let's practice naming this, and in order to do so, we would have to identify what elements are in here and how many of each. We have Cl, that's chlorine, and we have 2 of them. So since there's more than one at the beginning, we have to use a prefix to identify. So we would use the prefix di, so this would become dichlorine. And since there's one oxygen, this would be monoxide. Dichlorine monoxide. And our second one here, I'm going to go to the next screen, is SiCl4. Since we're going to identify our two elements. There's silicon and then there's chlorine. And since there's only one silicone, we do not use prefixes. So this just becomes silicone. Notice I do not change the name at all of the first element, silicone. And then how do I write 4? Well, the prefix for 4 is tetra. So I would write tetra, and then chlorine becomes chloride. So this becomes tetrachloride. So silicone tetrachloride would be the correct way that you would name that. And by the same token, if you are given the name, then you should be able to write the formula. All right? Then if you'll look on page 56 of the text, you're going to also see that there are some simple acids at the top in the table 2.4, like HF. The actual systematic name for that would be hydrogen monofluoride, but the acid name, acids, if they begin with hydrogen, then it's an acid. All acids begin with the element hydrogen. All acids do. So I know that this is an acid, and I'm going to identify it as such. And if it's a binary acid, remember what the word binary means. It only has 2 elements in it, just 2. So if it's an acid, then I'm going to start it with the word hydro. And that hydro indicates the hydrogen involved. So hydro, and then I'm going to name it with the other element involved. So fluorine becomes fluoric. And then I'm going to write the word acid. And all binary acids are named the same way. So if it's HCl, that's a binary acid. I'm going to name it hydro. And then chlorine becomes chloric acid, hydrochloric acid, and so forth. And then the last thing on here are something called empirical formulas. And this text only touches on empirical formulas. Empirical formulas can be very difficult to do, but for this text, we're just going to start with simple alkanes, and alkanes are hydrocarbons that contain only hydrogen and carbon and nothing else. So let's look at a very simple one. This is ethane that I'm writing for you, C2H6. An empirical formula is sort of like a fraction in simplest form. That's what it is. So an empirical formula takes a molecular formula. This right here is a molecular formula that says the actual components of everything that's in there, and it reduces it down. Okay, so this is going to take, the empirical formula is a reduced molecular formula. So we're going to take this and we're going to reduce it. You're going to ask yourself what goes into both 2 and 6, and that answer would be 2. So we're going to take and we're going to divide both of those by 2. And so the reduced formula for this, the empirical formula, would be CH3. And empirical formulas become useful for scientists and chemists when they are trying to identify unknowns. If you have an unknown sample, let's say at a plane crash site, or an unknown substance that was found in a lab or a site, a meth lab or something along those lines, and they want to identify what it is, it's very helpful to know the empirical formula. If you know the empirical formula, you can oftentimes identify what the substance is. So that's why you would need to know that. And you're just going to reduce, in our case, that's all we're going to do for right now. Now later on, we're going to learn how to write and find empirical formulas. But if you can know the empirical formula and you know the molecular weight, you can find the molecular formula. But for right now, that's all we're going to do. And I'm going to ask you to work some. It's much more important for me right now that you can write formulas of binary molecular formulas. That's significantly more important. And then I'm going to do one more PowerPoint for you this afternoon on how to write ionic compounds, formulas with ionic compounds, and learning your polyatomic ions. There's a lot of polyatomic ions that are out there, and you need to start learning them. So I'm going to stop for now. I'm going to give you an assignment to do, and you're going to start working on naming molecular compounds.